This is a video from section 1.7 in a linear algebra class. Let's take a look at problem 22. Let A equal the matrix 2, 0, 0, 0, negative 3, negative 1, 0, 0, negative 4, negative 6, 0, 0, 0, 3, 8, negative 5. All the entries above the main diagonal are all 0. And so that means A is a lower triangular matrix. And in lower triangular matrices and upper triangular matrices, it's very straightforward to tell whether or not A is invertible. And so that, in fact, is the question. Is A invertible? The answer is no. And notice, I'm circling the entries along the main diagonal, right? And the reason why A is not invertible is because at least one entry along the main diagonal is 0. You're done. As long as one entry along the main diagonal is 0, A cannot be an invertible matrix. Now, let's take a look at 23. Suppose A is the matrix 3, 2, 6, 0, 1, negative 2, 0, 0, negative 1, okay? And B is the matrix negative 1, 2, 7, 0, 5, 3, 0, 0, 6. And I want to know what AB is. So I'm going to take 3, 2, 6, 0, 1, negative 2, 0, 0, negative 1. And I'm going to multiply it by negative 1, 2, 7, 0, 5, 3, 0, 0, 6, right? And then what's going on? Well, if I look at the first row, I want the entry in the first row, first column. And that's going to be 3 times negative 1. Okay? And that's going to be negative 3. And then I want the entry in the first row, second column. That's 3 times 2 plus 2 times 5, right? So that's 16. And then I want the entry in the first row, third column, which is 3 times 7 is 21, so it's a little old school. 2 times 3 is 6, and then 6 times 6 is 36, right? And if I add those, 6 plus 1 is 7, 7 plus 6 is 13, write down the 3, carry the 1, 63. Sorry, a little old school. Then go to the second row. The first entry should be a 0. The second entry should be a 5, right? The third entry should be 3 minus 12, negative 9. And the nice part about AB, because remember, A is an upper triangular matrix, B is an upper triangular matrix, so all the entries below the main diagonal have to be 0. And then that very last entry should be negative 6. So it's really, really slick way. You know, when you have two upper triangular matrices, you know what the entries have to be below the main diagonal. So that's how we do 23. Let's take a look at 25. this one's a great question too. So if A is the matrix 4, -3, A plus 5, -1. So I want the value of A. That makes A, capital A, symmetric. Okay. So what am I going to do? I'm going to set A plus 5 equal to -3, solve for A. And then if I solve, I get A equal -8. And so when I replace A with -8, you will see that A has to be a symmetric matrix. Let's take a look at 26. So now, this one's a little tougher because A is 3 by 3. In the first row, we get 2, A minus 2B plus 2C, and then 2A plus B plus C, right? And then 3, 5, A plus C, and then 0, -2, 7. Now, this is what I would do, right? Now, I want you to pay attention to something. Look at the entry in the first row, second column. That entry has to be the same as the entry in the second row, first column, to be symmetric. So in other words, A12 has to equal A21. No choice. Which means A minus 2B plus 2C has to equal 3. There's no choice there. And then I want you to take a look at this entry. This is the entry in the first row, third column. That entry has to be the same as the entry in the third row, first column. In other words, 2A plus B plus C has to equal 0. Sorry for all the different colors. And then the entry in the second row, third column has to be the same as the entry in the third row, second column. In other words, notice that A plus C has to equal -2. Now, what I would do is I would set up the associated augmented matrix. 1, -2, 2, 3, 2, 1, 1, 0, 1, 0, 1, -2, right? That's what I would do. So over here, I'm going to repeat that. 1, -2, 2, 3. That's the first row. And then 2, 1, 1, 0. And then we get 1, 0, 1, -2. Okay. So I'm going to take -2 row 1, add it to row 2, put the result back into row 2. Then I'm going to take negative row 1, add it to row 3, put the result back into row 3. So I'm going to put this in row echelon form, and that's plenty. So we get 1, -2, 2, 3, 0, 5, negative 3, I think, right? And then negative 6. And then we get 0, 2, and then negative 1. And then the last entry should be negative 5. Now, what I would do, and we're not going to avoid fractions, unfortunately, is I'm going to take 1/5 row 2, put the result back into row 2, and then I'm going to take 1/2 row 3, put the result back into row 3. When I do that, I get 1, negative 2, 2, 3, 0, 1, negative 3/5, negative 6/5. Here, and we'll do this on the next page, make it easier. So we get 1, negative 2, 2, 3, 0, 1, right? And then I'm going to get negative 3/5, negative 6/5. For the second row, 0, 1, and then I'm going to get negative 1/2, negative 5/2. Okay, now I'm going to take negative row 2, add it to row 3, put the result back into row 3. And so when I do that, I get 1, negative 2, 2, 3, 0, 1, negative 3/5, negative 6/5, and then I get 0, 0, and then, so again, I'm old school, so I want 3/5 minus 1/2, right? And that looks like it's 1/10. Okay, and then I'm going to take 6/5 minus 5/2. So I'm going to come over here and I'm going to do, and I write it down. I'm not shy about writing things down like this. 6/5 minus 5/2 looks to be like negative 13/10. And then what I do from here is I'm going to do 10 row 3, put the result back into row 3. And then I'm pretty much done, right? So I get 1, negative 2, 2, 3. And then that's the first row. 0, 1, negative 3/5, negative 6/5 for the second row. And then for the third row, I get 0, 0, 1, negative 13. So what does that mean? I get A minus 2B plus 2C equal 3. And then I get B minus 3/5 C equals negative 6/5. And then I get C equal negative 13. So we know what C is right off the get-go. By back substitution, I get B minus, or I could say, if you don't mind, B plus 39/5 equals negative 6/5. So what I did was I replaced C with negative 13 in equation 2. And so B is negative 45/5, which is negative 9. And then A minus 2 times negative 9 plus 2 times negative 13 equals 3. A plus 18 minus 26 is minus 8 equals 3. And so therefore A equals 11. Okay. Now, after all that work, I can make my substitution. So A, now in the first column we get 2, 3, 0, right? And if I make my substitution for A, B, and C, it's just kind of a nice way to check our work. A is 11, so we get 11 minus. B is negative 9, so it's 2 times negative 9 plus 3, or actually 2 times negative 13. So A is 11, B is negative 9, C is negative 13. And then I get 2 times 11 minus 9 minus 13. It's just a nice way to check. 5, negative 2 for this entry, right? And then A plus C. So A is 11, C is minus 13. And then 7. And when I go to simplify this, right? 2, 3, 0 for the first column. 11 plus 18 is 29. 29 minus 26 is 3. So that's good. And then over here, I get 22 minus 22 is 0, right? Negative 2, 7. And that's what I wanted. So you can see that A is symmetric. And so those values I found for A, B, and C all work. And that's how you do problem 26. Let's take a look at problem 27. And then we can call it good for this video. Let A equal the matrix x minus 1, x squared, x to the 4th. For the first row, 0, x plus 2, x cubed for the second row, and then 0, 0, x minus 4. So A is not invertible. If x minus 1 is 0, x plus 2 is 0, or x minus 4 is 0. So if at least one of those entries is 0, A is not an invertible matrix. So therefore, A is not invertible if x is 1, x is negative 2, or x is 4. You're done. So A is invertible for all real numbers except negative 2, 1, and 4. You're done. So, in other words, for all real numbers x, so look, we're finding all values of x for which A is invertible. And for all numbers except negative 2, 1, and 4, A will be an invertible matrix. Okay, that'll conclude this video for section 1.7. We did 22, 23, 25, 26, and 27. Thank you.